Hi everybody, and I would just like to start by thanking the organizer for giving me the opportunity to make this presentation. So I'm a particle physicist from the University of Edinburgh, and I'm going to talk about lattice simulation energy efficiency, specifically focus on the GPU Nvidia A100 integrated in the Boole Sequana XS 2000 system. Some general goal, I guess these are some things that are going to be repeated during this session, but it's mainly about understanding the energy footprint of HPC calculation, and this serves other purposes, like understanding how to improve energy efficiency to help reaching net zero computing targets. Something which is a little bit more related to what's happening now with the energy crisis is to understand how to mitigate the impact of energy, surging energy prices on operational budgets and scientific outputs as a consequence. These are very general goals. There is probably an infinite amount of way to go about that. As a scientist, I like to think about that from a bottom-up approach because HPC workflows are very complex, and the way they consume energy is going to be very different from one workflow to another. So here I'm starting by my field of research, which is lattice QCD simulation, and to do a really domain and hardware-specific studies, and I'm going to discuss at the end. And I guess this is something we'll be very interested to discuss in general, how we generalize that to a less specific framework. Everything you're going to see is based on a report that has been commissioned by STFC and DIRAC. The report and all the associated data is publicly available, and there's a Creative Commons non-commercial license, and you can use the link here in the slides to access the data. Okay. So this is going to be the outline of my presentation. I'm going to start by presenting the grid library, since a non-specialist audience for this particular field of research, which is the software I've been using for this study. I'm then going to describe how I've been setting up, measuring the energy efficiency on our system. I'm going to show the results, and I'm going to conclude by some kind of analysis from a decision-making point of view of these results and some perspectives. So let me start by grid, and even before grid, let me start by speaking about lattice QCD. If you have no idea what lattice QCD is, I'll try to make a very brief slide about it, but it's a discretized formulation of the standard model of particle physics, which is the master theory beyond particle physics that describes the interaction between subatomic particles. This discretized formulation allows for Monte Carlo estimation, so stochastic evaluation of the so-called standard model path integral, which is the master equation. So essentially, again, if you don't know what I'm speaking about, most quantity in particle physics are eventually related to this formula called the path integral, and this technique allows you to directly evaluate this particular formula, and this allows ab initio or from first principle prediction of standard model observable. This is meant to produce reliable, free of approximation prediction in particle physics that can then be compared to experimental measurement, like in the LHC at CERN or in other collider experiments. This is currently one of the largest computer time investment as the DIRAC facility, and so it's a good workflow to start with to wonder about energy efficiency. So that's kind of lattice field theory as a scientific problem, now trying to kind of classify it more as a numerical problem. There is many things that can be computed in lattice simulation. It's fairly heterogeneous, but what is rather uniform is that all the numerical cost is generally dominated by solving something called the Dirac equation. And the Dirac equation is a sparse linear system, which is generally 4-dimensional or 5-dimensional, depending on the formulation which is used. And it got about 1 billion of variables. So this is one first component of lattice QCD. It's a numerical calculation with a lot of degree of freedom. Another unfortunate thing, which comes from just nature and the mass of particles in the universe, it's a system which is generally rather poorly conditioned, and so it has to be solved through iterative solver, which generally have some fairly sophisticated preconditioning. But mainly what you should get here is that the fact that it's poorly conditioned means that the iterative solver generally going to need a large number of iterations to converge. So it's a large number of degree of freedom, a lot of iteration. So it means that nowadays really state-of-the-art lattice simulation cannot be performed without large-scale parallel supercomputers. This is the only way to do that. And so scaling and parallelism in software design is a very strong constraint for us. In terms of intensity, I mean, sparse operator multiplication are generally bandwidth dominated. Here, for some mathematical reason I'm not going to enter into, which are due to the quantum nature of the theory, under that there is still a lot of, I mean, it's sparse, but there's still a lot of local operation to perform. So I would say lattice operators are generally somewhat balanced between compute and bandwidth bound. So the grid library is a library that has been developed mainly by Professor Peter Boyle from the University of Edinburgh, now in Brookhaven Laboratory, and I was with him at the start of this software also. And it's a C++14, fairly general data parallel C++ mathematical object library, which allow you to define large array across parallel machines and things like that. However, it has been targeted in many ways, specifically with lattice QCD calculation in mind. It is cross-platform. This is something that we're in the design from the start. However, through kind of template and code path selection, it does target architecture with specific optimization, and it supports a wide range of architecture. I think the most popular nowadays are x86, ARM, and Nvidia and AMD GPUs. And it optimally used while abstracting it from the user the three kind of form of parallelization, NPI, OpenMP, and also SIMD and SIMT. And last but not least, it is free and open source, and you can see the code and more information about it by following the links which are here. So that's for the software. The hardware I'm going to be using here is the Dirac-Toursa supercomputer in the University of Edinburgh. This is the supercomputer here. I mean, you can recognize the typical Atos blue strip of light behind it, and in front is the researcher team I'm leading in Edinburgh. Through a visit we did to the facility this summer. This machine in terms of configuration is, as I said, based on the Atos Sequana XH2000 system. It is made of 114 nodes. Each node contains 4 Nvidia A140 GPUs and 4 HDR200 Nvidia network interface. So putting things together, this is how grid performs on this machine, and I should say that the machine was actually procured and validated using grid as a guidance. So this machine was essentially designed to get the best performances and scaling for this specific software. And what you can see here, which is quite nice for a GPU system, it's because of the generous amount of bandwidth each node have, that the weak scaling is close to perfect after 2 nodes. And the performances are in the tens of teraflop per node. Okay, so that's a general presentation of kind of the context and the hardware. And now I'm going to describe exactly what type of testing was done during this study. So here I've been using a benchmark which is integrated in the grid library, which is called benchmark_DWF_FP32. And what this benchmark does is that it benchmarks a specific sparse matrix, which is called the Domenwall-Fermion operator, which is, without entering the detail, which is a typical matrix that needs to be inverted in an actual lattice calculation. And the FP32, as you probably guessed already, is making all this operation in single precision. For the study, I've been reserving on our system 2 entire racks over the 5 racks the machine has, and this is a total of 48 nodes, 48 GPU nodes, and so 4 times the amount of GPU cards. And yeah, that's it. And the way these nodes were populated with the benchmark is to have 2 16-node benchmark that were joining nodes from the 2 racks, and then 2 isolated 8 nodes. You could ask me why. This is a layout which is based on optimal communication topology, which is based on the way the network of the machine was designed. So basically, these blocks are the one we know are going to get close to peak bandwidth, network bandwidth in practice, and good scaling. Because you saw in the plot before, the weak scaling is almost perfect for this size, 8 and 16 nodes. Here in the whole energy efficiency study, I've been keeping the local problem size constant. So it means the benchmark running on 8 nodes is going to take exactly the same time on 16 nodes, essentially. And everything you're going to see in terms of performances, power, and all that is measurement which are done when the whole 2 racks are running according to this layout. So speaking about problem sizes, I've been using 2 problem sizes. So as I said, here it's actually a 5-dimensional lattice, but the 5th dimension is fixed to, I think, 16. But it's not the most important thing here. The most important are the dimensions which are actually being parallelized and distributed across the machine. And I use 2 sizes, one which I call C0. It's a random name which is related to a data set we're using in production. So this is actually the problem size C0, which is the most used on the day-to-day life of the machine, and it's 24 cube times 12 local lattice size. And I added another one, which is a bigger one, what I call log 32, which is a 32 to the 4 local lattice. And actually, you know, for the study, I just picked that size because it was kind of the next size. But now I realized that we're going to start production in the next months on lattices which have exactly this size. So this is also very realistic for short-term future research. So about power control and monitoring. So here the exercise how to reduce the power draw of the machine is going to be done through underclocking the GPUs. So we're going to put some lower frequency limits on the GPU, and this is something which is performed through the Nvidia SMI interface. And the idea would be to underclock the GPU down to their lowest frequency, and doing the scanning, see all the performances of the code evolve. So the A100, so this is something which is hardware fixed in the hardware, and the A100 GPU allow you 81, if I'm not mistaken, frequency settings going from 210 megahertz to 1410 megahertz by increment of 15 megahertz. And the default setting, if you don't do anything to the GPU, is to allow up to the maximum frequency of 1410 megahertz. And finally, monitoring power to kind of establish the energy consumption of the jobs. There is 2 sources of data. One is per GPU monitoring, which is also provided by the Nvidia SMI interface. And then there was a per rack, so it's a monitoring that only gives you the power draw of the entire rack. And that was done through a set of scripts and tools that was provided by Atos. And yeah, and this includes everything, right? So it means everything in the node, which is not the GPU, the CPU, the memory, but also the network infrastructure and the cooling pump, everything was into that. The only thing which is not accounted in the number I'm going to show is the storage, which is in a separate track, which I've not put in here in the figure. Okay, so let me go through the results. So I'm going to start by the kind of rawest form of data and try to go step by step to a more processed form data. Here is just what's happening on one node during. So it was a master node of one of the job. It was for the large problem size. Here the GPU has been limited to about 1 gigahertz. And that's what's happening during the benchmark. So you see the benchmark take about 550 seconds to complete. And the blue line is the power draw of the GPU you can read on the left vertical axis, and the orange line is the activity of the GPU. You see that can go up to a maximum of 400%. There are 4 GPUs in the node, okay? And yeah, and that's what happened in GPU during the benchmark. And as you can see, there is 2 clear phases. And let me not go through the technical detail of what the benchmark actually does. You can actually ask me the question after, but essentially it's benchmark two operator, one which is called dhop and one is called dhop even odd, which is the preconditioned version of the same sparse matrix, and it benchmark them in turn, and in between them it does some random initialization of data for the benchmark data, and this has this small idle period you see. It's just to prove that, you know, because with GPU it's always a bit tricky, it's just to prove that the GPU is indeed very active during most of the duration of the benchmark. This is the view from the rack power monitoring, so it's very different from, it looks very different from what I just saw, because the power monitoring is made by another server. So here what I just did is to record power during the whole scan of frequencies. And so what you see here is basically 81 repetition of something similar to that. And so it is the 81 benchmark for the 81 different frequency measurements. And you can see here the time is much longer, so it took about 20 hours to run this sweep. And as you can guess, I started by the lowest frequencies in the GPU up to the maximum frequency, and you can see the power draw of the racks to increase. And lattice simulation, maybe I should say, is really synchronous parallelism. So every node is supposed to do exactly the same amount of work. And as you can see, the rack 1 and 2, you cannot distinguish the change in power. So they're really doing the same thing. Okay, so now let's start to process the data a little bit. So these are the performances of the 2 operator for the 2 problem size in teraflops per second per node, depending on the clock limit on the GPU. And for the large problem size, you see that at the maximum default frequency, we go back to the 10 teraflops per second I've been mentioning before. As you go down in frequencies, you can see that, as expected, less throughput goes in the calculation, although interestingly, it doesn't happen in a linear way, right? There is clearly different phases in the scan. And one thing that allowed me to simplify things for after, you can see that the 2 different sparse matrix being benchmarked essentially have the same level of performances. So in the rest of the talk, when I speak about performances, I always take the average of these 2 operators to make things simpler. Okay, so this is the total power draw. So it's a kind of processing of the more messy plot you've seen before. The total power draw of the 2 racks versus the clock limit, and you can see that it does increase in an accelerated way as you go to the maximum frequency to reach about close to 100 kilowatts power draw for the larger problem size. Thanks to the 2 different power monitoring, you can play games of deduction and try to understand what different components consume in terms of energy. And here the blue line is the total energy consumption that comes from the Atos rack monitoring. The orange line is the aggregated power measurement from the GPUs only, coming from the Nvidia SMI measurement. And now I can do this non-GPU, the green line, by just subtracting the 2 other. And what's very interesting here is that you see that it's basically a constant. Okay, I mean, it increases a little bit, but it means that, well, maybe that's what one will expect or want. But as you change the GPU clock limit, essentially the GPU is the component that change its power draw the most. It's not completely obvious in my opinion, because it's a parallel, it's a synchronous parallel calculation, and there is constant communication, and as you go to faster performances, put more pressure on the network interface, more pressure on the CPUs to drive them, and so you could imagine there will be a significant changes, but no, really it's mainly the GPU carrying the variation. And by the way, this 25-ish kilowatts you see here of the non-GPU element, I measured the non-GPU element in a completely idle state of these racks, and it was about the same. So it's consistent also with the idle draw of the machine. And that's somewhat the main result plot. I mean, it's this bump you see here on the curve is exactly what you're looking for, and this is what I'm going to spend the end of the talk discussing, which is the energy efficiency against the GPU clock limits. And so the energy efficiency is defined in gigaflop per joule. So it's the amount of floating point operation performed for a joule of energy spent. It's equivalent to what the Green 500 call gigaflops per watt. I just removed the second from the units, but it's exactly the same unit that the Green 500 is using to rank system. And what you can see here is that the energy efficiency is higher for slightly lower frequencies than the maximal one. And so it is a proof of something which I think is generally well known, that the default setting of this processing chip is not optimal if it's set to, if it allows to go to the maximum frequency. Okay, so essentially, this plot could be enough and could be the result, and you could, pick on this graph saying, well, maybe you should go to 1 gigahertz because then you get more stuff done for watt hour spent on the machine. The issue, of course, is that there is one dimension not represented in these plots, that as you downclock the GPU, the calculation is going to take longer. It's more efficient, but it's still going to take longer, and that might be undesirable from a research point of view. So the conclusion here will be to discuss that a little bit. This is some kind of cost-benefit, if you prefer, question. And for this particular study, I've been privileging two different questions. Well, it's based on the optimization technical epsilon constraint, but without being too jargony about things, I prefer to just write the questions one would like to answer. One is what I call performance priority optimization. It's simply asking the question, what is the GPU frequency that minimizes the energy cost of a certain amount of work, but with at the same time a maximum negative impact of performances of a chosen threshold epsilon. So basically you're saying, I do not want, it's unacceptable for my users that more than 15% of performance are lost, and with this constraint, which GPU frequency is actually the most energy optimal? So this is one first question you can ask. Another question, which is more related to the current energy crisis, is assuming your epsilon is a cut on the energy cost of the system you want to enforce at all costs. So you say, I need to reduce my energy bill by 30%, period. And then the question is, what is the GPU frequency which with this constraint will give you the maximum performance despite the cut, right? So this question can be answered by doing this kind of landscape plot. So here I've been showing the relative performances of the code versus the relative energy cost of the code. And by relative, I mean always relatively to the default setting, which is the maximum frequency. So this point here, which is the maximum frequency setting, is exactly 100 coordinate, right? And you can see how you deviate from that. And what this allowed to answer the first question. So the first question was about limiting impact on performances. And for example, you say, I don't want more than 20% impact of performances. So you draw a vertical line here and look at all the solutions which are in this side. And well, you can automatize that, and that's what this plot represents. So this is here on the x-axis is the impact of performances you can maximally tolerate, and the y-axis gives you the optimal GPU frequency setting. And you can see something that was visible from the energy efficiency plot from the beginning was this bump, is that if you tolerate more than, if you can tolerate 10% impact on performances, then you can reach what is the absolutely energy optimal point, which is around 1 gigahertz, like I was showing before. All right, so this is actually pretty good news. I was hoping well, I was not hoping that. Let's say I was expecting something worse than that. 10% of impact of performances is fairly reasonable, and the amount of energy saving you can do, I have the exact figure in a slide later basis, something 16 to 23, 24%. I don't remember the exact number, but it's going to come after. This is the landscape plot that helps you making decision on more strict power cuts. And here I put it the relative median power draw during a given benchmark versus the relative performance. And typically here you say, well, I want to reduce that to 80% of the default cost. And you draw a horizontal line, and then you see all the solutions that remain that will achieve power energy consumption lower than this threshold. And you can also process that automatically. And this is essentially the answer with no power cut. You, of course, if you don't care about cutting power, you just set the GPU to the maximum frequency, and that's how you achieve the work the fastest possible. And here you can see what happens as you require higher and higher power cut. And you can learn something that, for example, for the low problem size, you will never achieve more than 30% power cut, because of elements I just described before. The GPU is not the only element drawing powers. There is an idle power, which is significant, and etc. All right, let me finish. So on this particular setup, meaning this particular software and hardware, I think I've been demonstrating that 16 to 24% energy cut are possible with higher efficiency. And this can be achieved with GPU frequency limits around 1 gigahertz, and this will have, which I think is quite positive, a moderate impact of 10% on floating point performances. And so I think the main conclusion is something that should be said a lot in the context of energy efficiency and computing, that default frequency setting for energy part are generally not energy efficient, and it's really worse for specific software, looking at downclocking component and see if you can get more work done per energy unit spent. Looking forward, what we're going to do, I was discussing that with Mark just before this workshop, is to experiment with lowering the default frequency. So simply, by default, user will be imposed to work at lower frequency, but also giving user control frequency limits through Slurm scripts, for example. And so if they need to overclock the system, they still can go back to the maximum frequency. But I think just having a default lower frequency might already have a significant impact on the machine consumption. I'm working on doing larger tests with more accurate power monitoring. Here, especially the rack monitoring was a very low frequency one, and I'm working with Atos to try to make that better. This is on a specific software that could not perform quite well, so I think it's still fairly representative of what's relevant at the end. But we should try to look at optimizing this type of studies through code base, and also, which is a much more complicated question, domains. I'm very interested by this aspect. I think it's a very interesting thing. Don't hesitate to talk to me about it, and just drop my contact details here. Yeah, that's all. Thank you very much.